Between 1990 and 1992, researchers in the UK collected data on traffic flow, accidents, and hospital admissions on Friday the 13th and the previous Friday, Friday the 6th. And here's this data. So we had a bunch of different locations, locations over here, but we're going to assume that the traffic flow in locations 1 and 2 are independent. We want to investigate if people's behavior is different on Friday the 13th compared to Friday the 6th. And one approach is to compare the average traffic flow on these 2 days, which is what these researchers did. And the data set represents traffic flow recorded at the same location in the same month on the same year, one from Friday the 6th and the other from Friday the 13th. So both of them being on Friday helps account for a possible confounding factor that traffic flow is different on different days of the week. Are these two things independent? No, right? Again, traffic flow might be different on different days. They're in the same location, so they're going to have a lot of the same traffic flow, people that go through that intersection on their way to work every day, stuff like that. So they are not independent. So we can't do a confidence interval for the difference of, we can't do a confidence interval for the difference of the means. Instead, we're going to do pairwise differences. So when two sets of observations are not independent, they've got a special correspondence. They are paired. Right? So each of these is a pair, the 6th and the 13th. And so to analyze paired data, usually what we do is we look at the difference in the outcomes of each pair of observations. So we take each pair and we subtract them. And so that is the information in this column is the difference, it looks like the 6th minus the 13th. Right, and it doesn't matter which order we subtract in as long as we do it the same for all of them. Just kind of ideally, you subtract them in the difference that results in the most positive values and least negative values, but that may just be my personal preference. So now we have one data set, right? It's this, right? So instead of having two sets of data, the 6th and the 13th, we've subtracted them, and now we have one set of data. So our parameter of interest is the difference on Friday the 6th and Friday the 13th in the number of cars in all intersections. For a difference of means, it would be if we were going to subtract the averages, right, that would be mu 6th minus mu 13th. That's not what we're doing here. We're not taking the average of all of the 6th and the average of all the 13ths because they're paired. Instead, we have one mean of the 6th minus the 13th. Or just, mu difference or whatever you want to call it. I'm generally in favor of subscript that makes it clear what your variable is, but whatever, right? So it's not a difference of means, it's just it's the mean of the differences, not the difference of the means. Our point estimate is going to be the difference, the average difference in the number of cars in sampled intersections. So X bar. Now the analysis is no different than what we've done before because we have one sample, right? That sample of differences, and we're going to construct a confidence interval for that data. So plug all of these into your calculator, get the mean, the standard deviation, and our n is 10, and then we can construct a confidence interval. We're going to assume that this is a random sample of differences. Our sample size is small and we don't know the shape of the distribution, so we would want to plot these and check for skew and outliers. It doesn't look too skewed. There's one really big one here. You got a small one here, but it doesn't look too skewed. It's probably fine. And here's the graph, right? It's a little bit skewed, but it's not extremely skewed. Good enough. The population of differences could be normal. Good enough, we'll go with it. Which of the following is the correct calculation of a 95% confidence interval for the difference between the traffic flow between Friday the 6th and the 13th? So let's go ahead and do our full 4-step procedure for this confidence interval. So we want to state the parameter is the average difference between the traffic flow, or the average difference in traffic flow between Friday the 6th and Friday the 13th. And traffic flow between Friday the 6th and Friday the 13th. Our confidence level is 95%. Our we already checked our conditions. We said that the data doesn't look skewed, so we can assume normality. We're assuming that it's a random sample, and the independence, because we are now using the difference of the paired data, now those differences are independent. So we check the conditions, we name the test. This is a 1 sample t interval for mu diff, right? So it's considered a 1 sample t interval because we only have one data set. That data set is the differences. So it's a 1 sample t interval, but it's for the difference of the two means, or we could call this, mu 6 minus 13 or something like that, right? It's 1 sample, but it's a t interval for the difference of the paired data. And then our general formula is the point estimate plus or minus the margin of error. And the specific formula is going to be x bar diff plus or minus the t critical value times the standard error. Right? The standard error being s over the square root of n, which was 1,176 over the square root of 10, which ends up being about 372, already calculated for us. So that's going to be 1836 plus or minus the t value. So if we go back to our t table here, all the way back. Actually, I don't think I have the t-table. I think that's way far back. But if you go back and look at the t-table, it's going to be for 9 degrees of freedom is going to be 226. And actually, it's this one because it's times our standard error. Or you can do the inverse t of 0.025, 9 degrees of freedom, and that should give you 2.26. So 2.26 times the standard error of 372. And that is going to give us, when we do that, we'll plug that in, and that gives us the confidence interval from 995 to 2,677. So, can we say that there is a difference in the traffic flow between Friday the 6th and Friday the 13th? Yes. All of the numbers in our confidence interval are positive. So it is not plausible that the difference could be 0. Which of the following is the best interpretation for the confidence interval that we just calculated? We are 95% confident that this interval captures the true average difference between the number of cars on the road on the 6th and the 13th. It's the average difference. It's not the difference between the averages. Right? That would be the difference of means. It's D. Right? That on average, there are 995 to 2,677 fewer cars in the road on the 13th than on the 6th. The way that I would write that, I would say we are 99% confident that the interval from 995 to 2,677 captures the true mean difference in the number of cars on the road on Friday the 6th and Friday the 13th. That would be how I would phrase it according to the kind of formula that we've used so far. All right, and so just for reference, these are our standard error calculations. So for a mean, it's s over the square root of n. For a proportion, it's p1 minus p over n. For two samples, you square these, here for proportions, you add them together. For means, you square this and add them together. Remember, that's an S1 squared and an S2 squared. You add the variances. And that's it.